In this video, I'd like to talk about the math question of the day for Sunday, June 11th, 2023. And with this problem, we need to find the Taylor series of this function f of x about an x value equal to -4. And Taylor series are typically taught in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And Taylor series can be a little bit complicated. Essentially, for some functions, we can find what's known as a Taylor series, which is a power series representation of a function. As a quick example, with the cosine or the sine function, we can find a Taylor series, which is really just an infinite sum that can allow us to evaluate or approximate that function at different values. So for the cosine of x, the Taylor series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, where the signs will alternate, and it's all the even powers of x. And whatever the power is, you divide by that factorial. Where remember that, let's say 4 factorial is just 4 times by 3 times by 2 multiplied by 1. So we need to find a Taylor series representation for this function f of x, this e to the minus 6x, about this x value of -4. And to do this, let me first paste in the formula for the Taylor series. We won't derive it in this video, so I will just show you how to use it. So when we can find a Taylor series of a function, we can write it as this infinite sum, where in its expanded form, notice that each of these terms is a different power of x. You can think of this term here as being x to the 0, since that's just 1. This is x minus a to the first power, but if you multiplied that out, it would just be x to the first power. Likewise, this is x minus a squared, so you would have a quadratic here. This would be the cubic term, then the quartic, and so on. You would have infinitely many of these terms, and it's a power series, so the powers of x increase. Where if we look at the coefficients on the different x terms, notice that they all involve the different derivatives of the function, where you can think of this as the 0th derivative, or just the actual function evaluated at a. This is the first derivative, this is the second derivative, and you always divide by whatever derivative you're taking, that particular factorial. So here we're taking the third derivative, so we divide by 3 factorial, and so on. This would be divided by 1 factorial, but that's just 1. And same for this one, this would be divided by 0 factorial, but 0 factorial is also equal to 1. So let's use this formula. We will essentially need to take the derivative of our function several times so that we can notice a pattern. And the most difficult part of the Taylor series is figuring out the coefficients that involve the derivative. But like I said, we will just take the derivative repeatedly. So let me make a little bit of room, and we can repaste in our function here. And let's start finding the different derivatives of our function. So we can say for n is equal to 0, we just have our function, which of course we can just write as f of x is e to the minus 6x, and we'll deal with this about x equals -4 once we find the pattern. Now for n equals 1, in this formula, we're just looking at this coefficient here, and specifically we're looking at the numerator first, and we'll deal with the factorials later. We plug in n equals 1, so we're looking at the first derivative of our function. So we find the derivative of this using the chain rule. For exponential functions, their derivative is just whatever you started with, but then we multiply by the derivative of our inner function, which in this case would be -6. And now we move to n equals 2. So the second derivative, we take the derivative of the first derivative. And this constant -6 will just carry along. But again, the derivative of the exponential function is itself, and we multiply by the derivative of the inner function, which again would be -6. And this -6 carries along, so now we have -6 multiplied by -6, and we can write -6 squared. Now we look at n equals 3. You might start noticing the pattern now, but we're looking at the third derivative, so the derivative of the second derivative. Again, we'll have this e to the -6x. This constant, -6 squared, will just carry along, and we multiply by the derivative of the inner function, which is, again, -6. So now we have -6 multiplied 3 times. And for the most part, it's a good idea not to multiply these out, since that way it might be more difficult to find the pattern. The main purpose of finding all these derivatives is to notice a pattern that we can generalize for each of these terms, each of these coefficients of the power series. So we'll do this one more time. N equals 4, though you can probably see the pattern at this point. We're taking the fourth derivative of x, and again we just rewrite the exponential function, and the derivative of the inner function again is -6. This -6 cubed carries along, so now we're multiplying -6 4 times. So we can generalize this. Let me just make a slight amount more room here. We can say that when we're dealing with just n, or we're taking the nth derivative of our function, we will still have that exponential function, and notice that whatever n was equal to, that's the power that we raised -6 to. So this will multiply by -6 to the nth power. But also notice that in our formula, we're evaluating this derivative at a. And in this case, our a value is -4. Whatever we're taking the Taylor series about, that is the a value that we're using. So a in our formula will be -4. So we'll need to take that nth derivative at -4. Let's do that up here. We want the nth derivative of our function evaluated at -4, and we're just replacing x with -4, so we have e to the -6 multiplied by -4, which is 24, and that's multiplied by -6 to the nth power. So this is our formula for the numerator of this coefficient, and we'll just divide all of that by n factorial. So our coefficient here will be this expression divided by n factorial. And we can actually start writing out our Taylor series now. Let me just make a bit more room here. We'll have that our function is equal to this infinite sum from n equals 0 to infinity, where we have our coefficient of the power series terms. We have that nth derivative evaluated at -4, which we know is e to the 24th multiplied by -6 to the n. I'll put the -6 to the n first, it doesn't really matter. Multiplied by e to the 24th, and then all of that is just divided by n factorial. And then we have x minus a to the nth power. And we know a is -4, so this is really minus -4 or +4. So we have x plus 4 all to the nth power. So this right here is our Taylor series for this function e to the -6x about an x value of -4. And if you want, you can expand this, plug in an n value of 0 for your first term, an n value of 1 for your second term, and so on, and you can write it out in its long form, or you could just match it up with the pattern. F of a, if we plug in -6 here, or excuse me, -4, that's just e to the 24th power. Then we would have the first derivative at a, this one, which is e to the 24 multiplied by -6, and then multiplied by x minus a, and then we would have the second derivative at a. And you can see the pattern will match up with what we have here. We would have -6 squared multiplied by e to the 24, but now everything's divided by 2 factorial. Then we multiply by x minus a squared. and so on. You can either match it up with this formula here, or you can just use the summation notation and just plug in an n value of 0, then 1, then 2, and so on. But this right here would be our final answer.